So assume I have obtained through some methods a function that is parameterized, but perhaps the parameter beta is known, as I said, by only ad hoc methods. And we believe the system output is equal to this plus noise. Right? We have data from the past, so we can estimate, we have estimated beta, so we can also estimate the epsilons. They are called the residuals. They are also the forecast errors. And here, if we can assume that the epsilons are independent, we can improve the prediction intervals if the assumptions that are traditionally made, like the one I made a minute ago, that it's Gaussian, therefore 196 sigma gives me an uncertainty bound. So if those Gaussian or even Laplace bounds are a bit shaky, not very certain, we can use another methods, a simulation-based methods that we have seen already last week. That's called the Bootstrap. So the Bootstrap consists in saying the best information I could have about the epsilons is the epsilons themselves, or their estimates that I have from the data. This, jointly with this theorem that we used already, this theorem was a theorem that we saw in the first week or so about doing a prediction for an IID sequence. If I give you n numbers, and I assume they come from some distribution that I have no clue what it is, but I think they're independent, give me a prediction interval for a new value that would be given to you. Do you remember how we did that? Well, we looked at a magic table that says, for example, if the number of data points is 100, then a prediction would be between the 2nd and the 99th at 95% confidence interval. So it's based on order statistics. We've seen that for the median, for the quantiles, but it works also for a prediction, for a coverage interval. If the number of data points is very, very large, then the thing will be very close to the 2.5% and 97.5%. But if it's not very large, it's a bit amplified. Those are the numbers that we obtain here. Well, we can use this theorem together with the idea of the Bootstrap to explain how to obtain a prediction interval. Concretely, here is how it would work. So once I have this model and I have estimated beta hat by some method, whatever, then I can estimate the residuals as the errors of the model here. Then I take eta and xi to be those quantiles given by my confidence level and the number of points that I have. Here the number of points that I have are t. I have t points and I apply this result with the first n points are the points 1 to n, and the next point, n plus 1, is t plus l. Not necessarily t plus 1, doesn't have to be contiguous. The only thing that matters here is that the thing should be independent. So for example, if I have 100 data points, I take all the residuals, I take the second and the last but one, and that gives me a 95 prediction interval for a possible future. Therefore, I will apply this deterministic part of my model, and for the random part, I will use the coverage interval here. This is simpler, or it's mathematically simpler. It's computationally a bit more complicated, but hardly. But the main difference here is I'm not assuming epsilon is Gaussian or Laplace or whatever. I just assume I had some reasons to fit a model of this type that gave me an estimate beta. And therefore, this is using fewer assumptions. Let's apply this to our example that we saw before. First in linear scale for the growth virus growth expansion. So the green line is the fitted one. The red lines are the error terms I obtain if I believe strictly in the model. The model was saying this is Laplace noise, and I have fitted Laplace noise. Therefore, here is the interval I would have. If I use the Bootstrap, I will obtain the blue line. It's a bit different. The Bootstrap always gives a bit different things because they come from the data. So the confidence in the prediction interval you have is more, I would say, more brute, not less refined. But we see they roughly of the same order. So the error we do on the prediction interval is small, which is appropriate for an error bound. This is the same as that, but now in linear scale instead of log scale on the y-axis. We see that it will give the correct feeling about the uncertainty of the prediction error. The bootstrap is asymmetric here, which means the distribution of my error terms was not symmetric. Whereas my noise model was assuming Laplace noise, which is symmetric in distribution. But when I computed the residuals, I had more often negative residuals than positive ones, right? Which is because I don't have many points, only a small number of points. Of course, the bootstrap is very, very crude, but still works well. And so that's a useful technique to have in your bag of tricks. I did the same thing here for this model here. I fitted the model to a sign, and then I said, okay, let me separate in my thinking the fitting from the forecast. For the fitting, I use whatever I think is appropriate or convenient, and I obtain a sign function. But now let me use the bootstrap to say something about the forecast, because I might not necessarily believe on the statistical property of the noise here, which makes sense here. I see the noise is probably more heavy tail than Gaussian. There are excursions that are not isolated. There is a number of points that are way beyond what would be expected here. So if I estimate the residuals and draw from the bootstrap, I obtain the lines, the crosses here. So the little crosses here that are quasi the same here. So for this example, we obtain practically the same thing, which is reassuring. That means that my Gaussian noise assumption here, this is coming from true data, it's not simulation, so Gaussian is suspicious because of that, but the prediction is fairly consistent, at least with this number of harmonics. Okay, don't forget mini project is coming soon. That's the end of our part one of this lecture. I split it into two parts because it's a bit long, which does not necessarily correspond to the splitting of the hours. We will now continue with a set of techniques. What we have seen was also techniques, but those are methods for, first, what is forecasting really? What does it mean to do a forecast? Overfitting, use of the bootstrap. Let's continue with methods that are typically associated with what is called linear time series. So linear time series work well for when you forecast things that are things like the examples I showed before, the traffic on an internet link, the consumption, the power consumption, although there I don't know which method works best. You will need to find in the homework which one works best. But of course, there are many different methods that have been used. The linear time series method are really ARMA models. So this one is very specific, I would say, to the classical methods. But before that, I think linear time series methods use a number of things which are called filters that are very useful, whatever the fitting method is. And as we will see, that's very simple and very powerful. So we will go through that, and I hope this will be, you will share my opinion that's easy and very powerful here. Again, the idea of doing a forecast is to try to remove from the data all the things that are deterministic. So the low-hanging fruits, if you will. So it's the pre-processing. In machine learning, it's well known. You first have to go from the real world to things that are called features. And depending on how you do it, you may have a good machine learning solution or not. Right? So here it's exactly what we're talking about. Before number crunching your time series, it's worth thinking about whether we can apply a number of pre-processing steps. Some pre-processing steps have to do with clustering and, for example, deciding whether this thing happened on a weekend or during a day. Was it a holiday? So the qualitative things which have to do with classification and features I'll not go too much into them. I will see another set of techniques that are more appropriate to this course because they're not covered in other courses that are called the use of filters. Like it's a signal processing thing. For this time being, we'll use signal processing interpretation. So a kind of pre-processing is filters, and we'll see the idea is to remove from the data all the deterministic patterns through a filter. And the filter will capture, in some sense, will remember the deterministic thing you've removed. Then you will have something that's pure noise. And about the pure noise, it will be hard to predict anything. So in the worst case, you just do Bootstrap or things like this with it. And then you reverse the filter from the prediction to obtain good predictions and prediction coverage intervals. That's the idea. But for that, we need to go through filter. Here is one definition of filter. It's a mapping from the set of finite length time series to itself. Does everybody, all of you, agree with that definition? Does it correspond to the definitions you've seen before of filters?
Finite impulse response type of filters.
Finite impulse response. Anybody heard of the word filter before? So filter is, in principle, a mapping from a set of signals. That might be this one or another one. The filters I'm using here are the filters we use in reality, the ones that are implemented in MATLAB or NumPy or Julia. Those are the filters with which we work. They act on a finite dimensional signal, and they map it to another finite dimensional signal. To simplify things, now there are lots of tricks in filters and traps, tricks and traps. Typically in signal processing, we often assume, for example, that a filter applies on a signal that is periodic. We will see that we do things on filters like differencing, computing derivative. When you compute the derivative of filters, if we have n data points, we have n minus 1 in the derivative. And that's embarrassing. You had n minus 1. One point is missing. What do you do with a missing point? So very often in signal processing, we say it's periodic. So if one point is missing, when we overflow, when we get to the end of the signal, we say, well, let's return to the beginning. It may make sense when you have, although I'm not sure that why the left side of the image would be the same as the continuation of the right side. But that's often done in signal processing. Here we will not do that. So we need to be aware of those conventions. That's the only thing that we need to be aware of. A filter is not understood to be the same by everybody. The complicated filters are the filters on continuous time. When we are in continuous time, things are very complicated. We enter the theory of distributions and Dirac and all that stuff. So that's the kind of things we'll stay away with. Here we're in discrete times. So filters in discrete times are just plain linear algebra, simple linear algebra. So that's the good news. That's the only thing we have to use. A filter is something that takes a time series, so a vector of data, and we will, in all of this, like MATLAB does it, in most functions, but not all, I will assume that the length of the filter is kept unchanged by all the operations we do on it. So we would need to add zeros. I'll explain how. A filter is also, is a linear thing, it's linear algebra, and it's also time invariant. Among all the linear algebra, that makes it special. So if we want filter, if we add the word time invariant to linear algebra, that gives filters. And causal, we will also, what it means. Causal means that if I interpret the vector as indexed by time, the output at index t depends only on the input up to index t, but not later. It doesn't depend on the future. So if I put time invariant plus causal and linear mapping that has this property, we call it a filter. There are, as I said, different meanings of the word filter. Sometimes causal is not necessarily used, but in our setting, like in the use in prediction, we will always assume it satisfies this property. So let's see a small catalog of filters. The very first one is the differencing filter. That's the discrete time derivative. So I take a sequence of numbers, y1 to yt. I index by t rather than n to remember that we think of it as time. Then a filter is a transformation of this, so that's a vector. I transform it into another vector, which is equal to the differences here. So it's given by so for some reason here I called y the input and x the output. So the output x satisfies xt is yt minus 1. That's the discrete time derivative. The only embarrassing thing is what do you do at the edge? When you have in MATLAB, if you do that and you give t equal 1, you will have an out-of-bound index. So whenever we are out of bound, we use the convention that we put 0. Right. Why not? But that's not innocuous. If I have a time series that has an average 20 everywhere, and I do as if the values that are unknown are 0, I'm altering the time series here. So that's a rule that we will use because that's the commonly used in that setting, but we need to remember it. In particular, we should see that the first output here is probably non-meaningful. The first value of the derivative is probably garbage compared to the others here. Nonetheless, that's very convenient because it will enjoy a number of very simple mathematical properties here. So it's a linear operation. For example, if I take 2, so y plus z means I have 2 vectors and I sum them coordinate by coordinate, and the output is the sum of is the sum here. So here that's a compact notation. This is a vector. It means the tth coordinate of this is equal to the tth coordinate of that plus the tth coordinate of this one. Interesting property of the differencing filter and why we use it for forecasting is this one. If my time series is equal to another time series plus alpha t. Alpha t means linear growth with respect to time. Growth or decay if alpha is negative. Right? If I take the difference of that, well, alpha t is itself a vector. The first element is 0, alpha, 2 alpha, 3 alpha, etc. So if I apply the filter of this, it's delta 1y is equal to delta 1z plus, by linearity, alpha delta 1 of t. What is the difference of t? It's 1. The difference between t plus 1 and t is 1. So it's equal to alpha, a constant alpha. So when I apply the differencing filter to a time series that has a linear growth or decay, we obtain a time series that is equal to this plus a constant. So the plus a constant, if this one was random and stationary, if you add a constant, it remains stationary. It doesn't have a growth. So delta 1 removes linear trends. That's our first example of why we use filter. If I have a time series that's growing, one way is to model the growth, like we did an hour ago by posing an explicit model. But another way, which in my opinion is more convenient, is to kill the growth, because we will not need to fit it, is to kill the growth and fit z. If we can invert, which we will see is in fact possible. If we can go back from z to y, then we will not need to model the growth, and not modeling is a radical way of killing the overfitting problem. Now if I do that multiple times, if I have a polynomial of degree 2, then it's easy to see that the delta 1 of a polynomial of degree 2 will be a polynomial of degree 1. And therefore, if I apply it twice, I will kill a trend of degree 2. So in general, applying it multiple times will remove polynomial trends. So that's one of the very, very useful tricks. If you believe something might have a moderate growth, then instead of fitting it with polynomials like we did before, I can kill the trend by applying delta 1 a number of times, work on the transform time series, and then hope that we can revert. There are trends, there are also periodic patterns. Periodic patterns are removed with, for example, this filter, which is called the De-seasonalizing or Roberts filter, which consists in taking the sum, which up to a constant is the same as the average, over the period s. If you believe your time series is likely to have a period of S. For example, the previous time series was the time series taken every 90 minutes. So there are 16 times 19 minutes in a day. So I believe this time series is a good candidate to have a period of 16. So what I can do is apply this with x equal to 16. So S is the period of this thing. So we take simply the sum over the past 16 values of x, right? And then we will see that if y is periodic of period S, then this will be the integral over a period, which is always the same if it's periodic here. So by linearity, if a signal is equal to something periodic plus something else, by applying the seasonal filter, I will kill the seasonal component because if a signal x is equal to y plus z, if I apply r to y plus z, I will have ry plus rz, and ry will be a constant here. So rs removes periodic component. So that's our second very useful trick. And now the question will be, can we combine those different tricks? We've seen how to remove trends, how to remove periodicity. It would be nice if we could remove everything at a time. There's an alternative to this one, which is called delta sub s, which is the derivative at lag s. So it's given by xt is yt minus s. Right? Again, with the convention that yt is 0 whenever we are out of band. This will be also killing the seasonal component, because if you're periodic of period 16, if you compute x of t minus 16, you will find 0. Always here. So that's another way. We'll see the relation between the two. It also removes the periodic components. Well, here is the relation between the two. Delta S is equal to Rs delta 1. What does a notation like this mean? Composition. So here we interpret delta 1 as a mapping, a function, or an operator. In mathematics, we call function any mapping. In signal processing, a function is typically a signal, and a system is a mapping from signal to signal. But mathematically, it's all linear mapping. So this is the composition of mappings. So there should be a little circle here. It's Rs composed with delta 1 here. Filters, we usually write them as a product, like we do for matrices. Remember, filters are linear operators, so we can use also the linear operator notation. So this means exactly this, that if I do first delta 1, then Rs, first delta 1, then Rs, is the same as doing delta S. Right? Proof, well, we can use the definition of delta 1. So let me establish what we're doing when we do this composition. Ooh. So I have a vector y, I apply delta 1, I obtain z. So zt is yt minus 1. Then to z, I apply x. So I do xt is equal to the sum of the f components of z. So that's it. Now z, I use its expression out of y, I obtain this expression. And we see that the adjacent terms are cancelling, except the first and the last. So we obtain yt minus s. Right. This is our first example of what we can call calculus of filters. The interest of filters is that we can do very simple calculus with them, much simpler than standard linear algebra. That's the good news. It's simpler. All the dirty tricks of linear algebra or the dirty problems of linear algebra. What are the dirty problems of linear algebra? That will not appear here. What are the things you don't like in linear algebra, or that cause problems? Non-invertibility, exactly. Here we will see very simple criterion for invertibility that doesn't require computing a determinant or a spectral radius or whatever. Also non-commutativity. A plus b to the power n is very complicated to write because there are all the double products of a and b and a, and etc. Here we will see that we can find ways around that. Well, to make sense of what I said, I can we map this to a matrix? A filter is not exactly a matrix because a filter, when we say a filter, we don't say what is the length of the system to which we apply it, of the vector to which we apply it. Right? So here, if I specify the length, if I say I do it over time series of length n, what is the, it's a linear system, so it has a matrix representation. If I use the convention, unlike what I wrote, because for calligraphic reasons, it's easier to write vectors as rows, but if I use the MATLAB convention that by default a vector is a column vector, what is the matrix representation of delta 1? And the correct answer is the majority choice, A. If you need to be convinced, well, I take a vector x, which I write the MATLAB way as a column, and I need to write a matrix such that at the end we obtain this here. So we'll obtain the generic term is minus xt minus 1 plus xt. So we find this matrix here. What is special about this matrix? It's lower diagonal, exactly. So it's a triangular matrix. So triangular matrix are good, right? If you need to invert them. Is it invertible? Is this matrix invertible? Yes. What are the eigenvalues? One, yes. So you see, though, we will not need to do complicated linear algebra with those matrices that are very simple. Let's continue. Our second filter was the de-seasonalizing filter. What is its matrix representation? Dirac on B, which is again the correct answer, for the same reason as, we saw before, right? So we see if we would continue longer, we will find that it's again a triangular matrix with 1 on the diagonal, and then there are 4 terms that are non-zero starting from the diagonal. Right? Is it invertible? Yes. So we've seen that if we can do delta 1 and R4, then we will be able to invert. Quiz on filters. And the majority says G, but the majority is not always right. So let's see. So the first one is correct. So the first one is saying Rs delta 1 is delta S. We saw that a minute ago. We proved it. Therefore, B is correct also, because filters, unlike general linear mappings, commute. We will see why in a minute, but that's the first thing to remember. The filters commute. Right? That's very good news. I mean, it will make everything considerably simpler. Why do filters commute? Well, we'll see that a minute ago. The third is false, so that's something to be aware of, not to fall into that trap. Let's check what it means. Delta 1 times delta 1. I mean, intuitively, if you take the derivative twice, you obtain the second derivative. That's the discrete time second derivative, which is not the same as the derivative at lag 2. The second derivative is something more complicated, is the derivative of the derivative, how fast the rate of change is changing. Right? Whereas at lag 2 is something a bit different. Right? Mathematically, we can verify that. We can compute delta 1, so I do z equal delta 1, so that x will be delta 1 z. So x is zt minus y zt minus 1. Z is itself a difference of y, so this is the formula we obtain. Yt minus 2, yt minus 1 plus yt minus 2 plus here. Even though it's a second derivative, there is a plus sign here. That's the formula that you perhaps have encountered in practice when we estimate a second derivative on a trellis, for example, when we do numerical analysis. Those are the kind of things we will do. Right? So that's the second derivative filter, which is delta 1 square. It's delta 1 times delta 1, compounded with delta 1, which is not the same as delta 2 here. So those are our first homeworks with filters, first exercise that we did with filters. I applied filters to this time series, my internet traffic time series. I did differencing at lag 1. So what do we see? We see that's very frequent. This time series perhaps has a small trend, but the trend doesn't seem to be obvious. So if a time series doesn't have a trend, very likely the difference time series will be centered around 0, which is what we see here. I difference also at lag 16 because I thought that there is a period of 16. Then we see that in fact it's true. Differencing at lag 16 is claimed to have which property? Two. If it's periodic, it's 0. But here it's not strictly periodic, but it's expected to remove the periodic pattern. So we had something that was very periodic. One way to capture that is to introduce the sine function and all that stuff. But here we use another method, which consists in killing the periodicity. And we see here we practically manage, right? This doesn't look like a periodic time series. It looks like an ugly one, but not periodic. Here it's still periodic, so differencing at lag 1 did not remove the period here and has exacerbated the peak here that was present here. And here I've applied both, lag 1 and lag 16. Right. And here's what I obtain. I obtain something that starts looking more like noise, that appears to be very random, that doesn't appear to be a pattern, except that once in a while the amplitude is growing. It's getting larger or smaller, but there doesn't seem to be any pattern. Well, that's the main idea, and that's the power of filters. If I go from this to that, I have destroyed practically all the periodicity, but since I can revert the filters, I will get it back somehow. We will see it. I have obtained something that looks like something purely random. Therefore, perhaps I cannot say much about this one, but that's good. If I cannot say much, it means it's pure noise. And I can get rid of it and just estimate perhaps only the amplitude and how bad it can get. Don't you ask a question here about how I did that? In which order did I do that? Does it matter? No. If we say filters are commutative, so if I do delta 1 then delta 16 or delta 16 then delta 1, I should get the same. Now, what I did here is I said, well, after all, when I have this, I can consider that as noise. I'm aware there are large deviations in the amplitude, but other than that, I don't see any pattern, so I treat that as noise. So this is random noise. In other words, I treat my data assuming that delta, which is delta 1, times delta s times y, is purely random, and here I'm doing a stretch of imagination. I'm assuming it's IID, it comes from the same distribution, which is not impossible given the size of my data. Certainly this distribution would not be Gaussian if I look at it here, because there are large values here. But it might be a distribution that has a heavier tail than Gaussian, perhaps Laplace, perhaps some other distribution. If I do this, and I do a prediction, here's what I obtain. I obtain the red curve here for a point prediction and the dotted curves for the prediction interval. So what do we see? Well, we see first, at least the point prediction is fairly good. In fact, the point prediction is much better than the point prediction I did before with fitting all my harmonics. Right. How did I create this? Well, we will see that in a minute. And how did I get the prediction interval? Well, what we could say is that the point interval is fairly good. The prediction interval is perhaps very large. It is too pessimistic. And perhaps this is where we'll stop for today. So the next thing we will do next week, or tomorrow, is to see how do we go once we have destroyed many things of the signal by applying filters, and we have something that's more simple to a lot of wind outside, something simpler to forecast. How can we reconstruct the forecast? So for that, we will need to manipulate the filters, so we will need to become experts of MATLAB's filters, which we will be after 1 hour tomorrow. Thank you very much.